Hello everyone, my name is Saber Jlassi and I'm a Senior Technical Director at Blizzard Animation. My current job consists of creating tools and scripts for lighting, compositing, and effects department, as well as working with production on solving challenging problems. I'm also a Houdini instructor currently teaching an 8-week course with CG Master Academy and producing various other online tutorials. And I spend a lot of my free time doing side projects using Houdini and Arnold and various other tools, and you can check some of my work if you go to vimeo.com/sabervfx. And today I'm going to be talking about creating a custom grooming system in Houdini from scratch. And we're going to be first creating the solution to produce a high-end VFX result, and then we're going to take that and convert it to for real-time rendering using two techniques. We're going to be creating cards, auto-generating cards with texture and passing that to real-time rendering, and we're going to use also Nvidia Hairworks to render the hair in real time. And the first thing we're going to be talking about is creating the actual grooming system in Houdini. And Houdini 16 has a lot of new hair tools, and I highly encourage you guys to explore those and use them in production. And the reason I wanted to create the system from scratch is to prototype something and basically show you guys how you can solve a very challenging problem with very little scripting in Houdini, and then we're going to take that to the next level and auto-generate cards with texture and pass that to in-games, and then we're going to look at the Hairworks system. So the first thing we're going to be talking about is the hair grooming for VFX. And what do we need to achieve this? We need three things. We need to be able to interpolate the hair and generate and expand the hair count from a given set of curves. Let's say we have 100 guide curves. We need to be able to generate 100,000 new curves that properly interpolate between all those guides. And then we need to be able to clump the hair and layer the clumps so we can have big, large, medium, and small clumps. And we need to be able to add variation to the hair. And so the first thing we need to talk about is the interpolation system, which I think is the most challenging problem in a hair system in general. And my starting point is going to be this. I have a geometry and guide curves. These were created by Tarkan Sarim. It's a great groomer, and he was kind enough to provide me this data to work with. And for the time being, we're going to ignore the geometry and only focus on the curves. And what I'm going to do in here is I'm going to delete all the points except the points at the root of each curve. And that will give me a point cloud that I can then mesh and generate what we call a connectivity mesh. And by isolating all the roots and running a to-diagonalize node in Houdini, we will be able to connect all the points using triangles. And this is the resulting mesh. And with this mesh, I will be able to know the neighboring curves. So I can take this triangle, for example, and know that I have 3 curves, and each of these curves I will be able to know the neighboring curves for them as well. So this is what the connectivity mesh is used for. And I'm going to delete everything and just focus on one triangle. So I'm going to isolate one triangle here, and I'm going to find all the 3 curves that are placed at each of these points. And what we need to do is we need to create curves here that are facing along the surface normal, and we need to interpolate them so that we fill all this space using with properly interpolated curves. And so what we're going to be using for that is we're going to create a barycentric coordinate on that triangle. And with this barycentric coordinate, we'll be able to know at each point of the surface how far we are from each of these points. And we know that we have a curve at each of these points, so if we create one here, we will be able to know how much we need to blend between this versus this versus this. And if we use that information, we will be able to properly interpolate between all these curves. And I'm going to use the UV coordinate to generate this barycentric coordinate data that we need. And you can Google it if you want to learn more about the barycentric coordinate. But what I'm going to do is I'm going to take point 0 and give it a UV coordinate of 0, 0, point 1 and give it a UV coordinate of 1, 1, and point 1 give it a UV coordinate of 0, 1, which will place it here. And point 2 we will place it here by giving it a UV coordinate of 1, 1. And so this is the UV coordinate of this triangle, and now we have the two coordinate that we need for the barycentral coordinate, we need the third one, and we can easily compute that by taking 1 and subtracting the uv.x and uv.y, and that will give us the third information that we need. And you can see here I'm using the color to preview the UV coordinate or the barycentric coordinate, and we can see that we have a nice transition between the various points here, and that's our barycentric coordinate. And so what we're going to do is we're going to scatter a lot of points on this triangle here, and by doing that they will automatically inherit all the attributes on the surface, all the point attributes on the surface. And if we then take a curve and copy it on these curves, on these points, the curve will also inherit all the information from the points. And what we need in this case is we need the barycentral coordinate. So if we loop over each curve and use that barycentral coordinate to blend shape between these three curves, we will be able to properly fill in the space between all these. We will be able to properly fill the space with properly interpolated curves. And so if we take our original input, this is the guide curves with the triangulated mesh, we can loop over each triangle and repeat the same operation. And by doing that, we can easily fill in the triangles with properly interpolated curves. And in this case, I've generated a version with 1000 curves, 1K, and another version with 3000 curves, and the high-res version with 86,000. And you can see we've successfully filled in all the space using properly interpolated curves. And I'm going to show the Houdini setup for this. So this is my starting point. I have the guides here with the geometry. I don't need the geometry here, so I'm going to simply focus on the guides, and I'm going to isolate all the root points, and I'm going to generate the triangulation mesh that I need. And so that's our mesh. And then we're going to scatter some points on this mesh, and then loop over each triangle here. And each time we isolate the triangle, we also isolate the curves that belong to that triangle. And I have a curve here that I'm going to copy on these points and then interpolate between all those. So let me show you the result here. I have a for each loop that loops over each triangle, and every time we isolate the triangle, the points that are placed on that triangle and the three curves. So if I dive inside here, you can see we have the triangle, and this is where I generate the barycentric coordinate that we need. I'm setting the UV coordinate here, and the last value is the third value is we're computing it here by subtracting 1 minus uv.x and uv.y, and we're previewing the barycentric coordinate as colors. And on the other side, I'm isolating all the curves, all the three curves that are placed at each point, and then I'm using that barycentric coordinate to interpolate between those three curves, and that gives me the result I need. And I've run this right now with how much points? Let's see, 5,000 curves. So this one will generate 5,000 curves, and I can simply increase the points here, and that will give me more curves. And I've already done that. I'm going to show you the result, which I showed already. So this is the final result, and you can see the original curves, and this is the 1K, 5K, and this is the 86K version. And if we zoom in, you can see that we have very nice distribution of the points, and they're properly interpolating between all the curves. So we're done with the interpolation. The next thing we're going to talk about is the actual clumping. And so here I'm showing an image with large clumps and small clumps, and I'm using this noise map to blend between these two, and this is the final result. And I'm going to show a video to explain the clumping effect that we want to create. So this is my starting point. These are the original curves, and what I want to do is I want to take a second set of curves and have these guides find the nearest curve close to them, and try to blend shape toward that. And we're going to use this linear ramp here, which starts 0 at the bottom and 1 at the tip. So 0 at the root and 1 at the tip. We're going to use that as a multiplier to how much we blend between this curve and its neighbor. And so if I hit play, you can see here I'm using the slider, and I'm basically blend shaping between these guides and their neighbors. And so we want to learn how to create that from scratch. And if we think about it, if we take one curve, it is made of multiple points, and each point has an XYZ coordinate. And what I'm going to do here is I'm going to pack all these XYZ coordinates of all the points into a long string. You can use arrays for this, but at that time I didn't get them to work, and I think they're in a much better state now. But in this case, I'm going to simply use Python to take the XYZ coordinate of all these points and simply create a string. And so this is the XYZ coordinate of the first point, the second point, third point, and I'm going to do that for all the curves. And if we run this operation on the 3K curves, I'm going to run the packing, so each curve has that string attribute that represents all the points. We can transfer that information from these curves into the high-res version. And the easiest way to do the transfer is to delete all the points except the roots, because this will give us the best result. And so this is the 3K version, and with that string attribute, once I have it as a one point attribute, it can delete all the points and still have my attribute. So this point here has that string attribute, and we know how the curve looked like before. So we have that information, we have all the details that we need about the curve. And so I'm going to transfer this to the high-res curves. And once I do that, I can loop over the 86,000 curves and unpack that attribute. So once we transfer this, I can say for all these curves here, go get that string attribute and unpack it. And this is the Python script for doing that. This is very simple. It's very basic Python code here. And by doing that, now each of these curves has the information about the curve that it can blend to. And so what I'm going to show next is the result of the high-res curves, and I'm blend shaping between the high-res curves and the data that we just transferred. And I'm using this ramp here that starts 0 at the bottom and 1 at the tip to basically multiply how much we're blending towards the clumps. And I've used a 3,000 or 5,000 curves here, and that's exactly how much clumps I have. And this is very powerful because I can decide exactly how much clumps I will get. And the other very powerful feature is that if you look at these curves, they have nothing to do with this. They're independent, and this gives me a great control over the shape of the clumps. So I can decide how the clump itself will look like, rather than just having something from the hair itself. And if we look closely here, we'll see that we have different size of clumps as well. And this is a very powerful technique, but I didn't explore it in this case, but you can see it's happening here. So what we can do with this is we can take the 3,000 curves and modify them so we can control the shape of the clumps themselves. And I used this version to generate I think 3,000 clumps, and I've used the 1,000 curves to do the same thing to generate bigger clumps. And here is a preview of that. And you can see I'm using the ramp here to decide how much I blend toward those guides. And this is the 1,000 curve. I'm previewing them as wires. And you can see we're getting some very interesting clumps. And so we have our clumping now, and all we need to do is we need to be able to mix between them. So the next thing is we're going to generate a noise map. So this is the large clump done using the 1,000 curves, and this is the small clump done using the 3,000 curves. And here I'm using a noise map to blend between these two results. And I can also use different colors other than white, and that will interpolate between these two as well, so it can generate even different clump that is a mix between these two. And I'm going to show the Houdini graph for this. And so I'm starting with the high res. This is the high res curves here, and I have the 3000 curves, and this is how much clumps I have. And the next thing is I'm going to do the packing of the attributes. So all these curves here, I'm going to pack all the point data so we know we can recreate the curve later on. And I'm going to delete all the points except the root, so we have that a string attribute that contains the position of the curves. And I'm going to isolate the roots of the 86,000 curves, and I'm going to transfer that attribute. And once I do that, I can unpack it. It's 1 second. Once I transfer that packed string attribute, I can unpack it on the high-res curves, and this is the result. And I'm going to show this is the result in action, and this is running in real time, and it's running this on 86,000 curves, and being able to do this in real time is very powerful. And you can see how I can change the clump shape along the curve length. So you can see here I'm not clumping anything at the root, but I can increase that easily. So I use the 3000 here to generate this version, and then the 1000 to generate the big clumps, and then simply generated a noise map, which is this one, and use that to blend between the various positions. You can see we have a mixture of large and small clumps. And so the next thing we want to do is we want to add some randomization to the hair. So it's super easy to do this in Houdini. We can use any point VOP to add any noise, but I have two deformers that I want to talk about. And the first one is the length variation, and all I'm doing here, you can see this is the original result, and this is the second after the length variation. I'm simply taking the last point of all the curves, and I'm offsetting it along the tangent of the curve. So we have a tangent information available to us on all these curves, and we can take the last CV and push it out and inward to vary the length of the curves. And because we have that, we have the clump information, the clump guides, we can do something very powerful. We can create a twist deformer easily. So here I have some curves to illustrate this, and this is the guide clump for those curves. And all these curves, they know about this information. It's placed somewhere here. This is just a preview, but it's inside these curves, and each one of these curves know about that curve. So we can construct an axis that is where the center is the clump guide, and the point that we're gonna deform is the point itself. And so by doing that, we can easily do something like this by creating by using a matrix and generating a quaternion. We can easily rotate the points along that axis and have this kind of twisting effect easily. And so this is I'm multiplying the result along the length of the curve as well, so you can control that. And I'm going to add a second one here to even make more complex shapes. And so this is running on a simple example, and I'm going to show it running on the actual guide. So here I've isolated few clumps, and you can see that because we have that information about the guide clump, we can easily do the twisting here on the guides. And I think that's pretty much it. I'm going to show a result with the deformer on and off. And so this is without deformation, and this is with the twisting, the length variation, and various other point deformers. And I'm going to show it in Houdini so it's easier to see. So this is the final result with all the deformation added. And I had to resample the curve so I have more points. If we zoom in, you can see the twisting effect here, and there is a lot of other deformers as well. It's very simple point deformers. We can see we have the length variation, and I'm going to show the original result with no deformers, which is this one. So we've successfully created the clumping. We've successfully created the interpolation, the clumping, and the variation. And I'm gonna show a render of this done using Houdini Mantra, and I'm using the default hair shader here, and a very simple light rig. And you can see we have the high-end, the high-res grooming here. So the next thing we're going to talk about is we're going to take this result and see how we can transfer it to real-time rendering. And there is two techniques for that. There is the card technique with texture, and there is the Nvidia Hairworks system. So we're going to focus on the card system. And what we need for that is we need to generate... one second. So what we need for that is we need to generate cards geometry that nicely flow through the hair curves. And then we need to give those cards textures. But in this case, we're not going to randomly give them texture in Photoshop. We're going to actually use the high-res hair and use Mantra to capture the texture details. And then we're going to pack the data and pass it to real-time rendering. So the first thing we're going to talk about is creating the cards themselves. And this is the result that we're going to be after. These cards were auto-generated from the high-res hair, and we're going to look at how to do that. So if we look at the hair itself, we can, what I want to do is I want to cluster it so that I can work with a cluster, a big clump at one time, and generate a card for that. I don't want a card per curve. I want to group each neighboring curves together, let's say every 300 curves, and then create a card for those. And so the easiest way to do the clustering in this case, or the thing that gave me the best result, is to isolate the tips of all the curves and then cluster those, and then copy that result back into the hair. So now I have clustering done on the tip, and this will give me the result that I want. And so if we take one cluster in this case and look at and see how we can create the geometry that nicely flows through this cluster. And what I'm going to do is I need to find the curve that always travels at the center of the cluster itself. And the way I'm going to do that is I'm going to isolate all the points at the root and all the points at the tip. And once I have that, I'm going to average all those points, all the points at the root and all the points at the tip. And that will give me 2 points. What I'm then going to do is I'm going to find the curves that are closest to these 2 points, and that will give me 2 curves. And these curves are the curves that nicely flow through the center. One of them starts at the root and one of them ends at the tip. And I don't need 2 curves, I only need one, and I'm going to blend between these two using that value that starts 0 at the bottom and 1 at the tip. And so we have that linear gradient. I'm going to use that to blend between these 2 curves, and that will give me 1 curve. And if I loop over all these clusters, and run that operation, we will be able to find the curves that nicely travels through the cluster. But this is not enough for us to create the geometry that will nicely flow through the curves. We only have the curve data. We need to find the orientation of the card. And for that, I'm going to take the head geometry, and I'm going to create some kind of a sphere around it, a geometry that wraps around the hair. And so I took a sphere and I ray projected it onto the head, and then I smoothed that out. And this, if I take the normal of that surface and transfer it to the hair, I will get the 2 products. I need to know the orientation of the surface that I'm going to be creating. So here I'm taking all the curves, and I'm taking the approximated surface that we've created, and I'm transferring the normals. So our curves have the normal information, and this is the normal transferred from the surface, and each curve has the tangent which flows through the curve. And if I compute the cross product between those two, I will get the vector that I need to extrude this card. And so I'm going to simply run an extrude operation, and that will give me the extrude operation will use this vector, and that will give me the card that I need. And if I run this operation on all the curves, I will be able to generate these cards. And so this is for the card creation process, and I'm going to show how it is done in Houdini. So this is the original curves, the original high-res hair, and I'm going to cluster it using that by isolating the tip and doing the clustering on the tip. So here I'm doing that. You can see I have the cluster information, and now we have successfully clustered the hair, so we can isolate one cluster at a time and work on it. So in this case I have this guy here, and I'm going to isolate the points at the root and the point at the tip, so these two, and for each one of those I'm going to find the point at the center. So these are the root. I'm going to average all the points, and that will give me the point at the center, and then I'm going to find the curve closest to that. And so I can do that, and then this is the curve closest to that point, and I'm going to do the same thing for the other points, and that will give me a second curve, and then I will use that ramp to blend between the two curves. So this is the root curve, this is the tip curve, and I'm going to blend between them. And now we have the curve that we need, and we have the tangent information. And so we need the normal from the surface. So what I'm going to do is I'm going to take the head geometry, and this is the sphere projected onto the head, and I'm going to transfer the normals from the surface onto the curve itself. And so you can see here we have the normal and we have the tangent. I'm going to simply compute the cross product and then run an extrude operation on it, and this will give me the card that I need. And if I run this operation on all the cards, I will generate the cards that I need. Cool. So the next thing we want to do is we don't want to texture these in Photoshop. We want to use the high-res hair, and we want to capture the details from the high-res curves. And so what I'm going to do is I'm going to isolate, we're going to create the texture. This is the result of the texture, and I'll explain in a second what is this. If we look at the cluster, we can isolate the high-res curves and the card that we've generated. And you can see that the card nicely flows through the curve. And what I'm going to do is I'm going to use Mantra and shoot reflection rays from the surface point along the surface normal, and whenever they hit the curve, whenever they hit something, they're going to reflect it back. So I'm going to use Mantra. I'm going to shoot reflection rays that starts from the surface position and travels along the normal. And if I do that, I will be able to reflect all this information. But this is only on one side. So I'm going to also do it on the other side by inverting the normals and shooting the rays back again. So I'll have two reflection happening. And if we run this and bake the result into texture, we will be able to create this. And this is the reflection of the curves onto the card. And I'm baking this result, the reflection onto UV space of the card, because they are NURB surfaces and they have perfect UV coordinate. And while I'm doing this, I can also query any extra information I need. So whenever the ray hits these curves, I can query the information back. So in this case, I have generated a random hair color, and this is the result. I also have the surface normals reflected, and these are from the result that we transferred here. And then I'm also computing the distance. So if a ray travels from here to here, it will return the distance of how far it had to travel to reach this point. And this one will return, for example, 1, and this one will return 0.5, and this one will return 0.2. And I can do it on the other side as well. And this will give me how far the ray had to travel to reflect that point. And I can use this in real time to do what we call a pixel displacement, to give that card its volume back in real time. And I'm also computing an occlusion path, and we have the tangent information on the curve, so I'm also reflecting that, and I can use this to shift the anisotropic specular in real time. And so if we run this on all the cards, we will end up with 250 cards. That's how much clusters I have. And it's a lot to take all these cards and assign them, each one of them a texture for real time. So what I'm going to do is I'm going to create a UV space where I take all the cards, the 250 cards, and pack them into one UV space. And this is the result of packing those textures. And what I'm going to do is I'm going to use the original UV coordinate, UV space of that texture to read in the texture, and then I'm going to write it back into this using this new UV space. And this way I can assemble, I can pack all the textures into one file. And I did this. This is the reflection of all the cards and packing them again. And this is the reflection of all the cards textures. And I'm creating an 8K image that contains all the cards textures. And then I'm going to export the cards as an FBX or an OBJ to Marmoset or real time. You can use you can use Unity, you can use Unreal. The easiest for me was to use Marmoset because they have a great shader that I was able to get a decent result with. So I'm going to save this file into a TIFF, and I'm going to export the geometry of all the cards with the new UV space, the packed UV space. And then I'm also going to pack all the other AUVs, so I don't want to lose that. So I'm also creating a separate file for each of these guys. And this is the result of using the geometry with the texture rendered in Marmoset. And this is running real time, and I was able to get 60 FPS using a 680 GTX, which is very old. And this has occlusion, translucency, and all kinds of real-time rendering features, and I think GI as well. And you can see I've used the subsurface shader here, and you can see the result by simply plugging in the textures. And I've used the anisotropic texture that we created, the tangent information, to shift the specular here. And I think I used the randomization also to vary a few things. I was not able to use the pixel displacement data they've created, but I know that Unreal has it. So I'm not an expert in real-time rendering, but this is the result that I was able to get by simply plugging in the texture. And so we've successfully created, we've successfully auto-generated cards from the high-res hair, and we've successfully auto-generated textures for the hair. And so this is basically a new approach that we can take to generate hair for games, and we can adopt a high-end grooming system and then have Houdini automatically generate the real-time version, the cards and texture for us to use. And so I think that covers the cards and textures. And the next thing we want to talk about is we're going to look at transferring this data to Nvidia Hairworks as well. And it's pretty straightforward. All we need to do is we need to generate a lower res version of the hair. Instead of 86,000, I'm going to generate a 10K version. And Nvidia Hairworks require a connectivity mesh for it to work properly, because it's going to expand the hair and it needs to know how the hair is connected. So we're going to look at how to create the connectivity mesh. And then we're going to import all the data into Maya and export it to Nvidia Hairworks. There is only a plugin for Maya and 3ds Max, so I had to go through Maya in this case to export the data that I need. And so for the 10K version, I'm going to take the 86,000 curves, the high res, and I'm going to generate a random number per primitive that goes from 0 to 1, and then I can use an if statement. If the value of that randomization is lower than 0.11, keep the primitive and delete everything else. And this way I will be able to get the, let's say, 10% or 20% or any percentage I need from the curves. So this is our 10K version. And then for the connectivity mesh, we're going to delete all the points except the points at the root. And I'm going to create a UV coordinate using spherical mapping. And I'm going to use the triangulate 2D with and give it the UV information, the UV attribute to connect these points, and that will give me the triangulate the connectivity mesh that Nvidia Hairworks needs. And so I'm going to export the curves as an alembic, and this the connectivity mesh as well as an alembic into and import that into Maya. And so this is the result. And all we have to do is use the Hairworks menu and create the Hairworks node here. And we need to create one join for the Hairworks to work. But it's very self-explanatory in the documentation. It's very easy to do this process. And then I've exported this into an APX project and loaded it in the Nvidia Hairworks standalone. It's called Artist Tools. And this is the 10,000 curves running in real time, and you can see that we can expand the hair count, so I have 97,000 here. And this is playing in real time on a 980 mobile version, and we've successfully exported all the data that Nvidia Hairworks needs from Houdini. And the portion where the step where we created auto-generated cards and textures, you can do that on any high-res hair. If you have any curves that you want to process them in Houdini, you can definitely do that. You don't have to create the hair in Houdini. And you can also use this Houdini to generate the data for Nvidia Hairworks. And you can see here there's a lot of attributes that we can play with to give the hair its physics, the correct physics. And here I'm adding a wind with some noise, and you can see that it's running in real time. And I think that's pretty much it for the talk. Thank you very much for watching, and if you have any questions, feel free to email me at my email address, sabervfx.com. sabervfx@gmail.com. Thank you for watching, and talk to you soon. Bye bye.